Hi everybody, welcome to the tutorial on our second unit, Nomenclature. Today we're going to be talking about functional groups and go a bit beyond what we've learned in this course so far. Here's just a quick refresher of our prefixes for carbon chains and prefixes when there's multiple of the same substituent. There are some examples at the bottom. And in case you forgot, let's go over our naming rules. When naming a regular alkyl chain, we follow 4 steps. First is to identify our longest carbon chain, which will be our main chain. Then we identify the highest priority functional groups and number our chain to give the lowest numbers possible. Then we name the chain and substituents based on their prefixes or suffixes. We've got a formula here. This is the location of the substituent on the main chain, the substituent prefix if there's multiple like di, tri, tetra, the name of the side chain like methyl, the location of our priority functional group or double or triple bonds, the root of our main chain, like pent, and the suffix, like ane, ene, oic acid, all, etc. Here is an example for you. We can see that we've got an alcohol group, so we're going to number the chain to try to give this the lowest possible number, because it's the highest priority substituent in this molecule. So that means we're going to go left to right. So this alcohol will be on carbon 2. We can also see we have 2 methyl groups on carbon 4. So because we have 2, we're going to give this a dimethyl name. So this will be 4,4-dimethyl 2-pentanol. And this follows our formula that we've got at the bottom there. Here's a refresher of the priority order of functional groups as well, and just a reminder of their names when they're on their main chain, and some pictures of them too for you there. One important thing to remember is that ether is a little bit different. They're always in the middle of a chain, so the shorter chain attached to an oxygen is given an oxy name, for example, methoxyethane or pentoxyhexane. Aromatic hydrocarbons are also super important, specifically benzene rings. As the main functional group, the chain will just get the ending benzene, for example, a methylbenzene. As a substituent, it'll be given the name phenyl. There's also different substituent names for when benzene is attached to different groups. When it's attached to alcohol, it becomes a phenol. When it's part of an ether, it'll be a methoxybenzene. And when it's attached to a ketone, it'll be a benzol. So now that we're all caught up, let's extend this. Are there any other kinds of functional groups that we haven't learned about yet? Remember the old chemistry joke about the 2 men who walk into the bar? The first one orders H2O and the second one orders H2O2, and the second one dies. This joke is about peroxides, specifically hydrogen peroxide, a deadly chemical. Peroxides are a main component in bleach, and everyone knows that you probably shouldn't be ordering that at the bar. Peroxides have 2 oxygens attached to each other with an R group on either side. You can see how hydrogen peroxide would look. It would have an H where those R groups are. In nomenclature, peroxides can be the main chains or substituents. As main chains, the suffix peroxide will be on the end, like hydrogen peroxide. As a substituent, we'll say peroxy. This is kind of like an ether. Remember, ethers have 1 oxygen attached to 2 R groups, and we'll call the shorter chain an alkoxy. The per in peroxide means 1 more, so it makes sense that we call it peroxy, 1 more oxygen. We won't really be talking about peroxides as substituent groups in this presentation, but it's just a good example in understanding how prefixes can tell us a lot about a molecule. So how would you name this peroxide? First, let's locate the peroxide, with the 2 O's in the middle. Now let's number the carbon chains coming off of each of these oxygens. We can see that on either side we have 2 carbon chains, or 2 ethyl groups. When we have 2 of the same group, we'll use the prefix di. So if we add the peroxide ending, this molecule will be called diethyl peroxide. Our next new functional group is called an anhydride. Anhydrides are made when 2 carboxylic acids combine to release water. Here is a visual of this. We have 2 ethanoic acids here. We know this because of our great knowledge about nomenclature, and these are going to combine to release water, which we can see happening here. This is going to result in a molecule that looks something like this, where 2 carbons are connected to a single bonded oxygen, and each carbon is also connected to a double bonded oxygen. This is what an anhydride looks like. An easy way to remember this is that the term anhydride means without water, and that's exactly what this molecule is. 2 carboxylic acids combined without a water. So how do we name these anhydrides? Well, remember, we're combining 2 carboxylic acids. Even though water's been released, we can still see the carboxylic chains, so to speak. In this anhydride formation, we can see two propanoic acids coming together to make this molecule. How do we know that? How do we know that they're propanoic acids? Well, we can number the carbon chains on either side of the single bonded oxygen. There's chains of 3 carbons on either side. Because 3 carbons means the prefix prop, it must have been 2 propanoic acids that combined to make this molecule. So how does that information help us with naming? Once that part's all worked out, the anhydride naming is pretty simple. The suffix of anhydride will always be anhydride, much like carboxylic acids always end with oic acid. We've got 2 propanoic chains, and if we add the anhydride ending to that, we can drop the acid of the propanoic acid because it's not relevant anymore. We will get propanoic anhydride. You might have one question about this. Why don't we call it dipropanoic anhydride? We have 2 propanoic chains after all. Well, when we think about anhydride formation, we know that 2 carboxylic acids have to come together. So there has to be a carbon chain on either side of the acid. When both chains are the same length, we just say 1 in the name because it's implied that the other one will be the same because we know we have to have 2 chains. So what do we do when the side chains aren't the same? It's pretty simple again. Here we have another anhydride. We can see by the pattern, the distinctive pattern of the oxygens in the middle. Let's count the chains on either side of the oxygen. So on one side we have 3 and the other we have 4. We know the prefixes for those numbers are prop and bute. So the 2 carboxylic acids that must have made this anhydride are propanoic acid and butanoic acid. If we drop the acid off of the name and add anhydride to the end and put them in alphabetical order because that's what we do in nomenclature, we get butanoic, propanoic, anhydride. So what's the point of learning all these functional group names? What's this going to do for us? All these functional groups are contained in molecules that many of us interact with every day. This case stays true with peroxides and anhydrides. So let's try out some real-world examples. All of us have experienced acne in our lives. This molecule is a main ingredient in the over-the-counter acne treatment that I know personally has really helped my skin, although it has bleached some of my face cloths. Let's see if we can name this one based on the new content we just learned. Think back to the beginning of our presentation. Remember those benzene substituents we went over? Take a look at the molecule. We can see 2 benzyl molecules on each side of the 2 oxygens bound in the middle. And let's label these just so we remember. Now what's the functional group in the middle? That's right, it's a peroxide. How do we name this? Take a minute to pause the video and try to work it out for yourself. We have 2 benzyls on each side, so we know to add the di prefix in front. We also know the molecule name is going to end with peroxide. So if we just combine these 2 things, we get the name dibenzyl peroxide. This is more commonly known as benzyl peroxide. It's what you'll see it labeled as in stores in products like these. This next molecule is found in Tylenol and is a key ingredient in creating the main ingredient that helps relieve pain. What could its name be? We've seen some examples pretty similar to this, so try to take a minute and work it out for yourself before we go through it. Does anything about this molecule look familiar? That's right, we have an anhydride group in the middle. 2 carboxylic acids must have come together to form this molecule. Let's work out what they were by counting the carbon chains on either side of the single bonded oxygen. On that side we have 2, and on that side we also have 2. We know the prefix that corresponds to 2 is eth. So the original carboxylic acids must have been 2 ethanoic acids. By dropping the acid at the end, we know that ethanoic will be the first part of our name. Remember, we don't say diethanoic because the fact that there are 2 is already implied. Only one step is left to finish the name. We just have to add the simple suffix anhydride. So this molecule is going to be called ethanoic anhydride. This is more commonly known as acetic anhydride. It creates acetaminophen, the main ingredient in Tylenol, when it combines with an amine. So we've seen in the last 2 examples that chemists sometimes make common names or simpler names to identify a molecule. Most of these have scientific reasoning behind them, but sometimes they can be a little more fun. I'll end this tutorial. Some may call it 3,4,4,5 tetramethyl-cyclohexane-2,5-dienone, but the more fun name that chemists have given it is penguinone. And as you can see, it looks just like a penguin, has a little ketone head at the top. It's a much more fun name, and it's just an example about how, although nomenclature can usually help us, there are sometimes creative liberties that take place. And that's the end of my presentation. Thank you so much for listening. If you have any questions, feel free to contact me at the email in the slide, and I hope you all have a great holiday break. See you when we come back in the winter.